Thanks for tuning into this Revision Zone Maths video. In this video, we're going to be looking at a variety of differentiation problems. So our first problem is actually a fairly nice thing to look at, which is we're given a function x times by e to the x, and we're asked to be able to sketch that function. Okay, so let's take a look how we might go about doing this. To begin with, let's consider how we would have done this problem before we saw anything on differentiation. So what we would do in that case is we would just make a table. We would say x is going to be our inputs, f of x are going to be our outputs, and we might just pick a selection of random inputs, and then I can work out the f values at those x values, right? And once we've worked them out, then of course the thing to do would be to just sort of go and plot them. So perhaps we can sort of go to a coordinate system and say we've got x and we've got y, and then we can sort of plot our function y equals f of x and we'd be done, right? However, since we have seen a lot of work on differentiation, we need not actually take this approach, and we can approach the problem in a much more analytic way, which would hopefully give you insight into how differentiation can be used for all sorts of things as well. So let me make a bit more room and let's try that. A good place to start would be to get a feeling for which quadrant this graph is actually going to be in, right? Or the graph of this function is actually going to be in. So we've basically got to consider cases. So let's take the case of, so call it case one, x actually being positive, right? So when x is positive, we know that, well, e to the x is obviously positive because e to the x is always positive. That then tells us that x times by e to the x has to be positive. So in other words, our f of x is actually always going to be positive, which means for all these x values here, what I'm going to have is I'm going to have y values being positive. In other words, we're going to have our graph lying in that quadrant. Now, likewise, let's consider case 2. So case 2 might look something like this. We can actually have x being negative, right? So what happens when x is negative? Well, in this case, e to the x is still going to be positive because e to the x is always positive. We know that. But of course, x is negative. So when I multiply these two, right, I'm going to get something which is going to be negative. So x e to the x is actually going to be negative. In other words, f of x is actually going to be negative, which means when I come to these negative x values here, and if I put them into the function and then get a y value coming out, the y values are actually going to be negative. Therefore, the graph of the function is actually going to lie entirely in that quadrant. Okay? Already, we've been able to get a big picture view of what's happening here. So let's think more systematically and try to figure out how the graph's going to behave. So the first thing we might actually want to do is we might want to work out, well, what happens as x gets larger and larger, okay? So as x tends to infinity, it's clear that f of x, well, if the x gets larger, then clearly f of x is just going to get larger, even if that thing there remains constant. But the point is, as x gets larger, e to the x gets even more larger. So this thing here is going to shoot off to infinity, right? And that's quite a cool thing. And in fact, what we're going to have is we're going to have the curve going up and up and up, sort of as exponential curves usually do, but of course faster than your most exponential curves because this is an exponential curve which is actually being scaled up by something in front. So let's consider a case of what happens as x tends to negative infinity, right? To be able to think about this, we might want to say let x actually be minus n, where our n is technically, say, positive. So since x is minus n and n is positive, then x is actually negative. So now we can actually say f of x is actually going to be f of minus n, which is going to be minus n e to the minus n, which is nothing other than minus n over e to the n. Okay, so this is reassuring because we see that there's a negative in front, so the whole thing here is going to be negative because of course our n is actually positive. And in a fight between a linear function and an exponential function is going to win hands down, right? So as n gets larger and larger, e to the n is going to get even more larger. So as n tends to infinity, so as n tends to infinity, what we're going to have is we're going to have minus n over e to the n is actually going to tend to 0. because the denominator is going to get to infinity quicker than the numerator in some sense, right? But this is the point. Since n goes to infinity, that's the same thing as saying x goes to minus infinity. And of course, the thing I've got on the right-hand side here is just the function f, right? So I can come back and I can say, actually, what that tells me is my f of x is actually, of course, is e to the x, is actually going to tend to 0. Now, this behavior here is telling us that there's actually going to be an asymptote on the x-axis. So on the negative half of the x-axis. We know that because as x gets larger and larger negative, then f of x obviously gets closer and closer to 0, which basically means that the curve's got to live in this quadrant and get closer to the x-axis, so there has to be an asymptote there, right? So since the curve is going to go up here, and then it's going to sort of come and get closer and closer to the x-axis here, there has to be some sort of a stationary point in between. So we need to work out what the stationary point is going to look like. So let's do that here. So we can say stationary point at dy by dx equals 0, right? But what is my y? My y is obviously just f of x, which is x e to the x. This is a standard sort of function. We can differentiate this using the product rule, and I'm just going to write down the answer because we should be able to just differentiate these things in a standard way now. So factorizing this, we have that. And of course, if I want dy by dx equals 0, the only way that's going to happen, right? If I set this equals to 0, the only way that's going to happen is that if actually x is minus 1, because e to the x is of course always positive. So that then tells us that actually if I come back here, then at some point x equals minus 1, I'm actually going to have a stationary point on the curve here, right? So with all this information, we can actually pretty much just go back and sketch our curve. So let's do that. So the graph's going to look something like this, in fact, and it's got to pass through the origin, and we can actually do a quick check to make sure it is going to pass through the origin. So let's say when x equals 0, we can work out what f of x is. So f of 0 is just going to be 0 times by e to the 0, but of course e to the 0 is just 1, so 0 times 1 is actually 0. So we've basically done the question, and I hope you would agree that doing all the analysis we've actually done here actually gives us better insight into the overall behavior of the function than just going to some table, putting in some inputs and getting out some outputs and just plotting the thing, right? So let's look at the next example. Problem 2 requires us to prove a couple of statements. So the first statement actually says that we have to prove that every cubic must have exactly one point of inflection, right? And interestingly, statement 2 actually looks at quartics. We have to prove that every quartic that satisfies this condition is never going to have a single point of inflection, right? So let's look at the proof of statement 1. So I want to start with a generic cubic, so I'm going to say y equals ax cubed plus bx squared plus cx plus d, where a better not be 0 because otherwise I don't really have a cubic, and of course here I should say where a, b, c and d are basically real numbers. We know that all points of inflection satisfy the second derivative actually being 0. So let's differentiate our cubic twice. So the first derivative is obviously just going to be 3ax squared plus 2bx plus c, and therefore the second derivative, I'm just going to get 6ax plus 2b, right? So I want the second derivative to actually be equal to 0, which tells me that 6ax plus 2b actually has to be 0, which tells me that x actually has to be minus 2b over 6a, which is minus b over 3a. So indeed, we actually have a solution. We have a solution. How do we know that's a sensible solution? Because we know that a cannot actually be 0, right? So I should say here, since a is not 0, then minus b over 3a and f of minus b over 3a is actually going to be our point of inflection where y equals f of x is our cubic, right? So we've managed to show that whatever cubic we start with, we're always going to have exactly one point of inflection because the key condition that defines what a point of inflection is only satisfied by one value of x. Let's move on and think about statement 2. So I'm going to say proof. And of course, in this case, we're working with a quartic. So our equation is ax to the 4 plus bx cubed plus cx squared plus dx plus e, where again a is not 0 because otherwise we don't have a quartic anymore, and where all these coefficients are actually real numbers. So again, the same condition has to apply. So I say all points of inflection satisfy the second derivative being 0. So we work out the second derivative. The first derivative in this case is going to give me 4ax to the cubed plus 3bx squared plus 2cx plus d. And therefore, the second derivative is clearly going to give me 12ax squared plus 6bx plus 2c, right? And I want to impose the condition that I actually want solutions to the second derivative being 0, which is obviously exactly the same as me saying I want 12ax squared plus 6bx plus 2c equal to 0. But here's the problem. The fact is, before we had a linear equation, and so that linear equation would always have a solution, and in this case we certainly have a quadratic equation. There is no way of getting rid of this x squared term out here. Let's just take a look again at what we're trying to prove for statement 2. We're trying to prove that if this condition is satisfied on the coefficients of our quartic, then in fact the quartic's going to have no points of inflection. So having no points of inflection essentially means that this quadratic here has no solutions, right? So what do we know about quadratics not having any solutions? We know that no solution happens when discriminant is actually negative, right? So in this case, we can write this down, we can write our quadratic down as capital AX squared plus capital BX plus capital C equals 0, where of course our A is going to be 12 lowercase a, our B is going to be 6 lowercase b, and our C is just going to be 2 lowercase c. So when we actually write down our discriminant, we say b squared take away 4ac is less than 0. That's exactly the same thing as actually saying 6b squared take away 4 times 12a times by 2c is actually 0. And what we're going to have, perhaps I can sort of write it quickly on the side, 36b squared is less than 4 times 12 times 2 is going to be 96. And then we have ac. If we divide both sides by 12, that gives us the same thing as 3b squared is actually being less than 8 AC, which is precisely what we wanted to show. So what we've been able to show is provided that this condition here is satisfied, then there is no chance for this quadratic to be 0, but that's the same thing as the second derivative to that quartic not having any solutions for the second derivative being 0. In other words, that quartic will never have a point of inflection provided this condition is satisfied. So we've been able to show exactly what we had to show. The striking thing here is the first statement actually says that every cubic must have a point of inflection, and the second statement actually goes on to establish a case of infinitely many different quartics which actually will never have a point of inflection. So that's quite interesting because something seemingly less complicated satisfies a condition, but something seemingly more complicated has cases where that condition is never satisfied, or that property is never sort of present. Let's move on to the next example. Problem 3, we're given a graph of some function. We're not told what the function is, but we see the graph, and 5 key points have been marked on the graph. And the question requires us to be able to figure out what's happening to the derivatives and the second derivatives of the function at those points on the graph. So how might we want to sort of address this? I think a good way to do it would be to actually organize our thinking in a table. So let's perhaps construct a table. Our points are going to be A, B, C, D, and E, and we want to be looking at the first derivative, we want to be looking at the second derivative, and perhaps reasons for our answer. The first thing I want to do is actually look at points that are easily identifiable as our stationary points. So we can see three of them there. So let me perhaps write that down. So this is a B is a local minimum, E is a local maximum, and D is a point of inflection. For these points, we can actually go back to our table and we can just say, well, the first derivative is just going to be 0 at B, it's also going to be 0 at D, and it's also going to be 0 at E. And because our B is a local minimum, then the second derivative actually has to be positive. And because E is our local maximum, then the second derivative actually has to be negative. And because D is our point of inflection, then the second derivative actually has to be 0. So the justification for these choices would be the fact that it's a stationary point and the fact that it's a min, the fact that D is a stationary point, and the fact that it's a point of inflection, and the fact that E is a stationary point, but it's actually a maximum. So we're basically left with 2 points. We're left with A and we're left with C. And it's quite easy to see that if I wanted a tangent to the curve at A, then the tangent's going to be pointing downwards, which means the gradient's negative. So I know that the first derivative has to be negative. Likewise, if I come to C and if I look at a tangent to the blue curve at the red point C, then I see that the tangent's going to be pointing in the positive direction, essentially. So we know that the gradient is actually going to be positive. So we've been able to work out the gradients, but let's think about what's going to happen to the second derivatives. We see that the gradient there is definitely negative, right? And we see that by the time the curve gets to this point here, the gradient's actually going to be less negative. So what's happening is the gradient's going to go from being more negative to being less negative, right? Therefore, the gradient has to be changing and it has to be increasing. So the second derivative is going to actually be positive. So we apply a similar analysis to the other point, and what we're going to say is actually if I come to C here, of course the gradient there is positive, but as we get closer to D, the gradient's actually going to be less positive. So what we can say is it's going to go from more positive to less positive. Therefore, it's got to be decreasing, so the second derivative has to be negative. And I should say here that I'm actually talking about the gradient. Of course, for our peace of mind, it's also worth looking at the other part of the curve for C, and we can see that even for sort of the part here, the gradient's going to be steeper than it is actually going to be there, right? So the tangent here is going to be steeper and it's going to be less steep there. So it's going to go from positive to actually something being a lot less positive. So it's going to go from more positive to less positive. Therefore, the second derivative has to be decreasing, so it's got to be negative. Problem 4 is quite wordy, so let's read through it to make sure we understand what it's asking us to do. Let C be the curve with the following property. At the point P, xy, on the curve, its gradient is proportional to the product of the x and the y coordinates. And it goes on to say, given that at point A, which is 4, 2, the gradient of C is a half, show that the curve C satisfies the following differential equation. Okay, so this seems rather wordy, but actually it's a really, really easy problem. So we're just going to solve this directly. we know that the gradient, in other words dy by dx, is proportional to the product of the x and the y coordinates, right? We're sort of told that here. So I know that dy by dx is proportional to x times y. But of course, if it's proportional, then there must exist a k, which is the constant of proportionality. So I can say that dy by dx is actually equal to kxy, where k is some real constant of proportionality. So we already know that our derivative is actually going to be of that form. Okay, so all we have to show is that our k would work out to be, say, a 16th, and then we're home. How we're going to do that? We're going to use the information that we're actually given, the fact that at the point A, we know that the derivative is a half. So I'm going to come here and say at A, which is 4, 2, we have dy by dx is actually a half, and that tells me that a half is actually going to be equals to k times by 4 times by 2, and therefore this just rearranges to give me k is equal to a half divided by 8, which is obviously a 16th. So we're basically home. So we say therefore dy by dx actually has to be a 16th xy, which is precisely what we wanted to show. So we've basically done the question. It is worth adding a remark, which is to say, usually at this stage we would go on to be able to solve this differential equation to work out what y is as a function of x explicitly. However, we're not asked to do that, so we'll just leave that for now. Problem 5 is our first attempt at a modeling problem, which basically says we're given a cylinder and we're told that it has a surface area of 600 pi. And the question requires us to figure out what's the largest volume that this cylinder can possibly have. Let's think about a solution. We know that we want to be thinking about surface area, and we know we want to be thinking about volume, right? So let's think about a cylinder. So it's going to look something like this. And if I take the height of the cylinder to be h, and if I take the radius of the cylinder to sort of be r, then I know the surface area is going to be, well, we're going to have sort of a circle on top and a circle on the bottom. So the circle on top is going to give me pi r squared, and the circle on the bottom is going to give me pi r squared. So the top and bottom faces are going to give me 2 times pi r squared. And then all the area of the side of the cylinder, this is a standard sort of thing, you can basically write it down as 2 pi r h. And if you're not too sure where that's come from, think of it this way. If I had a piece of paper where the distance on the side of that paper on the top, or say at the bottom even, that might be easier, or say 2 pi r, and obviously the height here is h, then the area of that paper is just going to be what I've written here, right? But the point is you can get a cylinder by taking a sheet of paper and by rolling it up. So the area of that side is going to be the same as the area of a rectangle where one of the distances is actually the circumference and the other distance here is actually just the height. Okay, so that's our equation for surface area. Now the volume of a cylinder is going to be cross-section times by height. So the cross section is just going to be pi r squared because I'm looking at it from the top down. So that's our cross section. And then our height is just going to be h. So we've got 2 formulas. We've got a function here for the surface area and we've got a function here for the volume. However, this is a 2-variable function or a function of 2 variables, and so is the function on the top. And what we want to try and do is actually get volume as a function of 1 variable that we're going to try and maximize. So let's do that. Perhaps I want to write this in a slightly more sophisticated way. I want to say my surface area function is a function of r and h, and it's 2 pi r squared plus 2 pi rh, and my volume function is also a function of r and h, and it's actually pi r squared h. And we can label this as 1 and 2 respectively. Now going back to the fact that we're told that the surface area is 600 pi, I can say my first equation actually tells me that 600 pi is actually equals to 2 pi r squared plus 2 pi r h. This allows me to rearrange for h, so I can just say 600 pi take away 2 pi r squared is 2 pi r h, and therefore h has to be equal to 600 pi take away 2 pi r squared divided by r. In this context, it's pretty clear that r has to be bigger than 0, otherwise we have no cylinder. Of course, I must keep my factor of 2 pi next to my r, so I'm just going to write that down. At this stage, what we want to do is we want to, since we have h purely as a function of r, we can go back to our description of the volume and convert it from being a function of 2 variables to being a function of 1 variable. So let's do that. So we can have v as a function of r purely is actually going to give me pi r squared multiplied by rh, which is 600 pi, take away 2 pi r squared, and the whole thing is divided by 2 pi r. And simplifying this, we see that the 2 pi, or the pi and the pi are going to cancel. So let's do that. So that pi goes away with that pi. And of course, one of these r's is going to cancel with the r we've got in the denominator. So that's that simplified. And at this stage, we can even simplify further and say how many 2's go into 600? Well, that's going to be 300. So perhaps I can sort of write that out here. So I'm going to get 300. And how many of these 2's are going to go into the 2 here? Well, that's just going to be 1. So I'm just going to have 1 here. And everything else is just actually going to remain. So I'm going to have the pi, I'm going to have the r squared, I'm going to have a pi here, the negative is going to remain, and the r at the front is going to remain. And of course, we've managed to take care of the entire denominator, so we're not going to have a denominator here. This simplifies to just give me 300 pi r, take away pi times by r cubed. And we've managed to get a function which is just a function of r. So we've got to work out the stationary point, but the stationary point is going to be at v prime r equals 0. Okay, well, what's v prime r? We know that v prime r is going to be 300 pi take away 3 pi r squared. And when we set that equal to 0, that tells me actually my 300 pi has to be equal to 3 pi r squared, which tells me 100 has to be equals to r squared, which indeed tells me because we want r to be positive, we take a square root and we get r equals 10. So we've actually been able to work out a solution, and our volume is going to be maximum at r equals 10. So I'm going to stick that in, and we can just evaluate our volume function. So we're going to get 300 pi times by 10, take away pi times by 10 cubed, which is 3000 pi, take away 1000 pi, which is of course 2000 pi. So this is going to be the maximum volume that's actually going to be attainable. Okay. It is worth doing a quick check to make sure that r equals 10 actually gives us a maximum. So we're going to apply the second derivative test. So let's quickly do that here. So I want to differentiate the function v twice. So we've already differentiated it once and we've got that. So we differentiate that now, which gives us v double prime of r is simply going to be minus 6 pi r, right? And needless to say, when I evaluate this at 10, I actually get minus 60 pi, which is a negative, which means our stationary point is actually a maximum. And so our solution is complete. Problem 6 is another modeling problem. It's a rather interesting problem. We're given a circle and it has radius r, where obviously r is non-zero. And the question is, what's the largest rectangle which may be inscribed inside our circle? Okay, so in other words, what we want to do is we want to maximize the area of the inscribed rectangle inside that circle. So let's work on the solution. So we might want to start with actually just having some random rectangle inside our circle. And of course, we need to have some understanding of there being a center to the circle. So we can actually go away and start to consider line segments from the center to the circumference. Now, let us label, say, the horizontal distance here to be x and the vertical distance here to be y. And of course, we're told that the circle is of radius r, which means that our distances here are both going to be the same, and they're actually just going to be r. Unsurprisingly, the area of our sort of blue rectangle is going to be a function of x and y because it's going to be the base times by the height, so it's just actually going to be xy. Now, what we need to do is we need to convert this and we need to express this as a function of one variable. How we're going to do that, we're actually going to use a little bit of Pythagoras so we can come back to our diagram and drop a perpendicular. And since this is a perpendicular, what we can actually say is whatever that distance there is, let's call it A, and whatever this distance here is, let's call it B. We can say A squared plus B squared has to be equal to R squared. Now, it should not come as a surprise that actually A is nothing other than a half x and B is nothing other than a half y. That's quite clear. So what we can actually go on and say is actually a half x squared plus a half y squared is actually equal to r squared. In other words, x squared plus y squared is actually equals to 4r squared, which tells us that my y is going to be 4r squared take away x squared, and I'm going to have to take the square root of everything. Since we're dealing with lengths, then I want my x and y to be positive. I should have said that here. My x and y are both positive, so I only just take the positive square root in this case here. But of course, the advantage of what we've now done, since we have a relationship between y and x, we can actually go back to our function and replace the y in terms of x. So I can say my area function, purely as a function of x, is actually going to be x times by the square root of 4r squared take away x squared. And the slightly nicer way of writing that is x times by 4r squared minus x squared all to the power of a half. Okay, so since we want a maximum, so we seek a maximum point on the function a of x, then what we're going to do is we're going to find the stationary point, which is obviously going to be a local max. We do that by differentiating a and setting it equal to 0. Well, what's the derivative of a? We're going to have to apply the product rule to this because we've got a function there and then we've got another function there. It's fairly standard. I'm going to differentiate that and then write that down. So differentiating x just gives me 1, and then I write the other function down. And now I'm going to just write down x and differentiate the other function. So it's going to be x times by a derivative of the function in the bracket is going to give me, by the chain rule, a half 4r squared minus x squared to the minus a half times by negative 2x. And this can obviously be simplified. 4r squared minus x squared to the half. Take away x squared, 4r squared minus x squared to the minus a half. And this thing here is, of course, a fraction. So it's x squared over 4r squared minus x squared to the half. So what we can do is we can combine this term and this term with a common denominator, and what we end up with is as follows. So we end up with 4r squared take away x squared to the half times by 4r squared take away x squared to the half over 4r squared take away x squared to the half, take away x squared over 4r squared take away x squared to the half, and now we have just 4r squared take away x squared all over 4r squared take away x squared to the half, which is nothing other than 4r squared take away 2x squared all over 4r squared take away x squared to the half. Let's make a bit more room and continue with this calculation. So we have our derivative and we just want to set this equal to 0. And obviously if a fraction is equal to 0, the only way to have that happen is if the numerator itself is actually equal to 0. So what we're going to say is we must have 4r squared take away 2x squared has to be equal to 0, which tells me 4r squared has to be equal to 2x squared, which of course tells us that r squared, or 2r squared even, has to be equal to x squared, and as a result x has to be the square root of 2r squared. Because we want x and y to be positive, so I'm just going to take the positive square root and it's going to give me root 2r. Okay, so we've actually got a value for x. Since we have a relationship which says y is equal to square root of 4r squared take away x squared, I can actually put in what my x is to be able to get my y. So my y is actually going to be also 4r squared take away x being root 2r, and I square that, and simplifying this I get 4r squared take away 2r squared, and obviously the whole thing is square rooted, which again just gives me 2r squared all square rooted, which is again root 2r. So in other words, let's write that down. We have x equals root 2r, and that's the same thing as y. So the shape which maximizes area is in fact a square. Okay, so what will the area actually be? The area is going to be, say, xy, but obviously we know what xy is. It's going to be root 2r and root 2r, which is actually going to be x times y, so it's going to be root 2r times by root 2r, which is going to be 2r squared. So this is quite interesting. What this tells us is if we go back to our circle, and the circle has radius r, the biggest area you can actually get is the same thing as basically having two lots of these sort of squares somehow inside our circle, right? So this is r, so that square here has area r squared, and then this square here also has area r squared. And what the solution of the problem tells us is the largest rectangle we can have is in fact going to be a square. Not only that, it's going to have area equal to the sort of area that I've shaded here. Let's quickly check that our solution is actually a valid solution in that we have a maximum point and not a minimum point. So we need to go back to our area function and we need to differentiate it twice. But because we already have the first derivative sort of above, I can just write that down. So let's do that. So it's going to be 4r squared minus x squared multiplied by a half. So perhaps I want to write it like this. So I can use the product rule to differentiate this and not quite the quotient rule, which is obviously slightly harder work. Right, so in that form, we apply the product rule and we say we want to write down the first thing and differentiate the second thing. So we do that. 4r squared take away 2x squared, and then the derivative by chain rule is going to give me a minus a half, all times by 4r squared take away x squared, all to the power of minus 3 over 2, all times by minus 2x. And then what we do is we write down this thing and we differentiate the other thing. So let's do that. So 4r squared take away x cubed, or x squared rather, all to the power of minus a half, times by the 4r squared differentiates to give me 0, and the negative 2x squared differentiates to give me negative 4x. Okay, so let's simplify this. So upon simplifying this, what we actually get is we get 4r squared, take away 2x squared, and all of that is multiplied by positive x times by 4r squared, take away x squared all to the power of minus 3 over 2, and then all of that is take away 4r squared, take away x squared to the power of minus a half, but obviously there's a 4x at the front. Let's evaluate this at our value of x, which is obviously root 2r. Now, you should notice that when I actually put root 2r into here, what I'm going to get is I'm actually going to get 2 times by root 2r squared, which is actually going to be nothing other than just 4r squared. So in fact, what I have is I have 4r squared here, and I have take away 4r squared here. So in fact, this entire term here is just going to go to 0, okay? So I can save myself a lot of work, and I can just say the first part is just going to give me 0, and in fact, the second part is going to give me minus 4 times by root 2r, and then brackets, 4r squared take away root 2r squared all to the power of minus a half. And indeed, when the dust settles, I get minus 4 root 2r, and the inside of the bracket is the usual thing, which is 4r squared take away 2r squared. So I'm just going to get 2r in there, or 2r squared in there even, with the following power. But of course r is positive, so that's positive, and that thing there is positive, so the whole thing there is positive, but there's a negative in front, which means the overall thing is actually negative. And that's telling me that my second derivative is negative at my stationary point, which means in fact what we actually have is the stationary point is actually a maximum, and so the solution we've worked out is perfectly valid, and that's the maximum area that actually any rectangle can have inside a circle of radius r. So we can move on to the next question. Problem 7 is a standard related rates problem. This is again a modeling problem. So in this case, at time t, we're told that a particular cube has area A and volume V. So by area, we of course mean surface area. And we're told that the cube is actually experiencing some sort of expansion, and because it's expanding, then its sort of surface area is going to increase and its volume is going to increase. And the question tells us that the rate of change of its surface area is actually 2 units per unit time, and we have to figure out what the rate of expansion of the volume is. Let's think about a solution. So we know that the rate of change of the surface area with respect to time is actually 2. I'm not going to worry about the units. And we actually need to work out the rate of change of volume with respect to time. This is what we need to work out. So we see how are we going to relate A to V, and of course we know that ultimately all of this is tied up to some sort of t. So we can actually do this by using the chain rule. So we can say dv by dt can be written as dv by dA times by dA by dt. Okay, so what I need to work out is I need dv by dA. Well, to be able to do this, we actually need to relate the volume to the area. So I know what the volume is. If a side length of a cube is x, then the volume is going to be x cubed. And at the same time, if the side length of a cube is x, then the surface area of the cube is going to be 6x squared, because it's pretty clear that if one side is actually x, then all sides are basically going to be x. And unsurprisingly, a cube's going to have 6 faces, so we see the 3 in front of us, and then the other 3 are going to be behind. So in fact, the total surface area is going to be 6 lots of these squares. Okay. Now that we have this, we can basically use equation 1 and equation 2 to work towards getting a formula for dv by dA. Okay. So we can in fact use the chain rule again, and we can say dv by dA is the same thing as dv by dx times by dx by dA. And in fact, using the reciprocal rule, we can rewrite this as dv by dx times by 1 over dA by dx, right? Which of course it can just be written as follows. So now this is very, very straightforward, because from our equation 1, we can basically say that dv by dx is just going to be 3x squared. And from equation 2, we can actually say that dA by dx is just going to be 12x. So we can put these in. So we say 3x squared over 12x, which gives us x over 4. And of course, throughout this, we need not worry about x being 0, because we know that our x is basically going to be positive, because we've got some sort of a cube, and it's got to have a side length which is non-zero. So as a result, what we can actually say is our dv by dt we can go back. It's just going to be x over 4 times by dA by dt, which is obviously just 2, so it just gives us a half x. So we've been able to work out a description for our rate of change of volume over time, and unsurprisingly, what we can say is the rate of change of volume over time is actually dependent on size of cube. Okay, so the bigger the cube, the faster it's going to expand according to this model. Let's take a look at the next example. Our last problem is another standard modeling problem. So in this case, we're told that because of the weather, a pond starts to freeze, and the thickness of the ice on the surface of the pond is measured by a variable called x, and t is keeping time from the moment that the pond began to freezing. And we're told that the rate of increase of x is inversely proportional to the square of x, right? And the question requires us to figure out what the function x is as a function of time. So let's see how we're going to do this. We know that looking at the key point here, which is the rate of increase is proportional to the inverse of the square, we can come and say that dx by dt is actually going to be proportional to the inverse of the square of x, okay? So from that, the proportionality tells us that there has to be a constant of proportionality. So we can say that dx by dt is actually equal to k over x squared, where k is some constant of proportionality. And at this stage, to be able to answer this question, we basically have to solve this differential equation. However, I don't actually want to solve this differential equation using standard methods, so I'm going to sort of argue more open-endedly. I'm actually going to say, let me rewrite that differential equation in a slightly different form. So I multiply through it by x squared, and of course where our k is just some real number, some constant. So at this stage, the key thing to keep in mind is this thing here looks very much like the sort of thing that comes out of implicit differentiation, right? So what I would ask you to do is to have a think about this. So if I take y equals a third x cubed, right, and imagine that I actually want to differentiate both sides with respect to t. This might seem a bit wacky, but do bear with me and you'll sort of see what I'm trying to say. So when we do that, of course, this is the same thing as the left-hand side is just going to be dy by dt, but the right-hand side is going to cause us problems if we don't use the chain rule or implicit differentiation. So using sort of the chain rule, what we can say is we actually just differentiate our third x cubed function with respect to x, but then we multiply everything by dx by dt. And of course, a third x cubed differentiates to give me nothing other than just x squared, right? And then the dx by dt is just tagged on the side. And it is worth saying that this thing here is the implicit differentiation part, or as some would say, the chain rule part. Now look what we've managed to do. We have managed to get exactly the thing we have on the left-hand side of our earlier differential equation in this form, actually out on the right-hand side here. So what we can do is we can go back to this left-hand side here, and we can replace that thing that I've just highlighted in blue or marked in blue with this thing here, right? Because they are completely equal. So I can say dy by dt is actually equal to k. And now this is such an easy thing to solve, because what this is saying is we have some curve and the gradient of that curve is a constant. Well, if the gradient of that curve is a constant, then the curve has to be a straight line. So my curve has to actually be kt plus c, which is a straight line. And this is basically our solution. The only catch is we don't want it in terms of y, we actually want it in terms of x, but we know what y is in terms of x, so I can go back and just fill that in. So actually I can just say it's a third x cubed is equal to kt plus c, and we've actually worked out our solution to the entire problem. This is the function. Of course, k and c are constants to be determined. We would need to get some experimental data to be able to figure out what K and C are going to be in this case. But for the purposes of this problem, we need not actually worry about that. So with that, I'd like to bring this video to an end. Thank you for watching. We hope you found this useful. Please let us know in the comment section as to what you would like to see more videos on. Do hit the like and subscribe buttons. And as always, we'll see you in the next video.